Question 2, complex numbers. We're given u here. We're asked to show that u is equal to 0 minus 1i. So we're multiplying top and bottom by the conjugate of the bottom, which is minus 3 plus 2i. So if we do the top line, this minus 2 by minus 3 and so on. So we're going to get 6 minus 4i minus 9i plus 6i squared. That's what the top is. That's going to be minus 6 and plus 6 cancel. We're going to get minus 13i on top. On the bottom, we're going to get, well, the i's cancel, we know that. So minus 3 by plus 3 is 9. Write out the minus 6i plus 6i just to show the examiner you know what you're doing. And then we have minus 4i squared, which is equal to 9 plus 4, minus 4i squared, minus 4 by minus 1, which is equal to minus I, which is equal to 0 minus 1i. Rewrite what you are asked to show it's equal to. We normally write the complex numbers in two parts. Part B is actually quite simple. In part 2, we're just asked to evaluate conjugate of u, and the conjugate of u will be 0 plus 1i. So part A, nice and straightforward. So the approach to part B, if 1 minus 2i is a root, let's say that 1 plus 2i is a root. If we add these together, we get 2 for the sum, and if we multiply them to get the product, we're going to get 1 minus 2i by 1 plus 2i. Similar to part A, the i's will cancel, so we're going to get 1 minus 4i squared, which is equal to 1 plus 4, which is equal to 5. So the product is 5. You all know that these quadratics can be written as z squared minus z by the sum of the roots plus the product. If you don't, you should. So to create my box method, I'll put my quadratic on top, z squared minus 2z, and then plus 5. And this quite quickly shows me yes, that is the dog snoring still. My first term of my cubic and my last term. And on the outside, I'll change colours. Z by z squared is z cubed. Actually, we can get the last root straight away. Minus 2 by plus 5 is minus 10. So let's just see that the rest work. Minus 2z squared. Z by minus 2z is minus 2z squared, which do add up to minus 4z squared. Minus 2 by minus 2z in here is 4z plus 4z, and z by plus 5 is plus 5z, and they add up to 9z. So you can see that it does work. So the last factor, be careful with the factor in the roots, is z minus 2. So the last root is z is equal to 2. Z is also equal to 1 plus 2i. And z is also equal to 1 minus 2i. Not the only approach you can take. You could sub in z is equal to 2 here and show that it equals 0, and then factorize your quadratic using the quadratic formula to get your two complex roots. You'll get these guys, obviously. This question deals with modulus. The modulus of z minus w, show it's equal to w minus z. And we're given z and w in terms of a, b, c, and d, and I. So z minus w, what's that equal to? It's equal to a plus bi minus c plus di. That's equal to a minus c. We put the real parts together, and then plus I times, we're going to have b minus d. And the modulus, if we just jot off to the side, what's the modulus of 1 plus 2i? Well, it's the square root, it's Pythagoras, 1 squared plus 2 squared. So it's the real part squared. So the modulus of this, I'll just put the modulus bars on, is equal to, it's equal to the square root of the whole thing. I'll just put the square root at the beginning, maybe, just so I don't have to draw a big line. So just assume we're going to have square roots on both sides, so I can kind of cancel them out. So we're going to get a squared minus 2ac plus c squared if I square this guy. Now if I square this guy, we're going to get plus b squared minus 2bd plus d squared. So this is equal to the square root of a squared plus b squared plus c squared plus d squared minus 2ac minus 2bd. If we do the other one, we should get the same answer. So the modulus of w minus z is equal to c plus di minus a plus bi, which is c minus a plus I times d minus b. So the modulus of this guy is equal to the square root of, if I square this guy, I'm going to get c squared minus 2ac plus a squared. And if I square this guy, I'm going to get plus d squared minus 2bd plus b squared. And you can see here that 1 is equal to 2, 1 is equal to 2, therefore the modulus of z minus w is equal to the modulus of w minus z.